Welcome back to this next video in which we are discussing hemostasis. Okay, so we've now been through the complete hemostasis pathway. What I now want to turn our attention to is looking at a few examples of bleeding disorders. Now, in bleeding disorders, the hemostasis pathway is not going to occur correctly. There's going to be some sort of problem with the hemostasis pathway, and therefore, if you cut yourself and you have a bleeding disorder, rather than the hemorrhage ceasing because hemostasis takes action, instead what will happen is you will just continue to bleed and bleed and bleed, okay, and hemostasis will take much longer to take action, so the hemorrhage will continue for a much longer time than it should, and this of course can be quite dangerous because you can lose a huge volume of blood potentially. Okay, so what examples of bleeding disorders then are we going to look at? Well, we're going to start off by talking about the hemophilias. Okay, so there are two major types of hemophilia, called Hemophilia A and Hemophilia B. Okay, now of the two, Hemophilia A is the more common than Hemophilia B. So if someone is suffering from hemophilia, it's more likely that they're suffering from Hemophilia A than Hemophilia B. Hemophilia A and B have very similar mechanisms that underlies the problem with the hemostasis process, as we'll see. Now, we'll begin with what's the problem in Hemophilia A. So Hemophilia A is also called classical hemophilia. So if someone's talking about classical hemophilia, that just is another way of talking about Hemophilia A. And the reason that there's a problem with the hemostasis mechanism is that in Hemophilia A you have a deficiency in functional factor 8. Okay? Now note I say a deficiency in functional factor 8, not necessarily an absolute deficiency in factor 8. You might still be producing factor 8 and have Hemophilia A, but the problem might be that all of the factor 8 that you're producing isn't actually functional. It doesn't perform its role properly. There's something wrong with it that means that it doesn't work. Alternatively, of course, you could be producing very little of it. That could be the problem instead. But the important point here is that the amount of factor 8 that is actually functional, that is actually capable of becoming active and performing its normal role, is far too low within the blood. So Hemophilia A is caused by a deficiency in coagulation factor 8. Now, let's just bring back up my picture here of the intrinsic coagulation cascade here and remind ourselves of the function of factor 8. So remember, factor 8 is converted to factor 8A, and this must form a complex with the activated Christmas factor, factor 9A here, along with calcium, on the surface of an activated platelet to form this complex that we call the 10As, which is the enzyme complex which is going to activate factor 10. Okay, so if you have a deficiency of functional factor 8, then this isn't going to happen. You're not going to be able to form the 10As, and therefore the intrinsic pathway is completely broken. So because of this deficiency of functional factor 8, the intrinsic coagulation cascade is no longer functional in people with Hemophilia A. Okay, that means that in order to turn fibrinogen into a fibrin mesh to produce a hemostatic plug, you only have the extrinsic pathway now able to do that. The intrinsic pathway is gone. Okay, so that means that the amount of fibrin mesh that you'll actually produce in your hemostatic plugs is going to be hugely reduced. And understand this, the fibrin mesh is extremely important for making the hemostatic plug strong. The platelet plug on its own, those cross-linked platelets cross-linked by the glycoprotein 2b/3a and the fibrinogen, that's very weak. The fibrin mesh is what holds everything together and keeps it very strong. Okay, so if your fibrin mesh is compromised because the intrinsic pathway is no longer functional, then you're going to produce much weaker hemostatic plugs, and therefore you're going to have problems actually plugging the hole in these damaged blood vessels and preventing the hemorrhage, which is why you will bleed and bleed and bleed, and it will take you much longer to actually produce a functional, viable hemostatic plug that can actually stop the hemorrhage. Okay, so that's what happens in Haemophilia A. Now let's go on to Haemophilia B. So Haemophilia B, as I say, is the rarer of the two, and this is also called Christmas disease. And that should give you a clue as to which coagulation factor it is going to be that is affected in Haemophilia B. Okay, so the mechanism's very, very similar. It's just deficiency of one of the coagulation factors. Okay, and of course this is Christmas factor, factor 9. So Haemophilia B, or Christmas disease, is a deficiency of functional factor 9. That's what it's caused by. Too low functional factor 9. So again, just like I said with Haemophilia A, it might not necessarily be that you are making far too little factor 9. It might be that all of the factor 9 that you're producing is just not actually functional. It's not capable of actually doing the job that you intended it to do. Okay, so there are multiple different mechanisms by which you could get a deficiency in factor 9. It could be that you're just producing far too little of it, or it could be that you're producing lots, but it's just not functional. Okay, so Haemophilia B then is caused by a deficiency in functional factor 9, and let's bring back up our picture of the intrinsic pathway again to remind ourselves of what factor 9 does. So it's the exact same stage as with factor 8 here. Factor 9 became factor 9A, and it was one of the components of this 10A's complex here with factor 8A and the calcium on the surface of the activated platelets. So if you don't have factor 9, then again you completely shut off the intrinsic coagulation cascade, and the only way that you can convert fibrinogen into a fibrin mesh is via the extrinsic pathway, which means that the amount of fibrin mesh that you're actually going to produce now for your hemostatic plugs is going to be hugely compromised, and therefore your hemostatic plugs are going to be much less strong, and they're going to have much more difficulty in actually preventing hemorrhage. So it will take you a much longer time to actually stop the hemorrhage, and therefore you end up with a bleeding disorder where when you cut yourself you bleed for much longer than is normal. Okay, so that is Haemophilia A and Haemophilia B, and those are the two main types of haemophilia, okay, caused by deficiency of functional factor 8 and deficiency of functional factor 9 respectively, and these destroy the intrinsic coagulation cascade, leaving only the extrinsic coagulation cascade to convert fibrinogen into fibrin meshes, and therefore you end up with much weaker hemostatic plugs being produced. Okay, right. Next example that I want to give of a bleeding disorder is if you suffer from liver failure. Okay, so in liver failure, the liver starts to fail the body. Okay, it starts to no longer perform its function well enough to keep the body alive, basically. Okay, so liver failure is where the function of the liver is starting to fail the rest of the body, and it's putting you in mortal danger. Okay, so in liver failure, of course, all the coagulation factors that are produced by the liver are going to no longer be produced at the correct level. So if the liver is failing, then you're not going to have the right level of coagulation factors in your blood because they're all produced by the liver. If the liver's not doing its job properly, then it's not going to be chucking out the right number of these coagulation factors. So the coagulation factor level will go down in the blood, and of course if all of the coagulation factors have gone down in the blood, then pretty much everything's going to have problems, because even the formation of the platelet plug requires the fibrinogen to cross-link the platelets. Okay, so you're going to have problems with forming of even the platelet plug, and you're certainly going to have problems with the intrinsic and extrinsic coagulation cascades and producing a fibrin mesh. So truly, your hemostatic plugs will be hugely weakened by liver failure, and therefore again you will end up with a bleeding disorder where if you cut yourself you will bleed for much longer than you should. Okay, and the final bleeding disorder that I want to mention, which is going to be very important for us to understand in order to later, when we go on to the video on anticoagulants, understand the mechanism of warfarin, is vitamin K deficiency. Okay, why is vitamin K so important in the production of coagulation factors? Okay, why is it so important in the normal hemostasis pathway? Okay, so this has to do with this amino acid gamma-carboxyglutamate, so I'm going to explain this now in full detail. So we have seen that certain of the coagulation factors, specifically coagulation factor 2, 7, 9, and 10. These were the ones I pointed out to you. Okay, so coagulation factor 2, 7, 9, and 10. All of these had this special amino acid called gamma, so that's a Greek symbol for gamma. You can write out gamma in full if you want. I'll just denote it by its short symbol, carboxyglutamate. Okay, they had this modified special amino acid. Now, this isn't a normal amino acid. This isn't one of the ones that will have a tRNA dedicated to it and which can be put in by a ribosome into a protein. This is a modified amino acid. It's a modification of glutamate, which is a normal amino acid. So what you do is you produce your protein, and then what you can do is go along and modify certain glutamate amino acids into gamma carboxyglutamate amino acids in a way that I'll discuss further in a moment. Okay, now these these coagulation factors here, coagulation factor 2, which remember is the name for prothrombin, coagulation factor 7, which remember is the one in the extrinsic pathway, which binds to tissue factor, coagulation factor 9, we've just been discussing that, and coagulation factor 10, both very important in, well, this one's important in the intrinsic pathway, this is important in both the intrinsic and extrinsic pathway. Okay, all of these have this special amino acid, gamma carboxyglutamate, in, and moreover, this amino acid is extremely important for binding to those calcium ions, which then also bind to the phospholipids of the activated platelet surface. So let me just get back up my diagram and we'll discuss this. Well, I'll point it out again. So here, look, here is 9A, and we've got the calcium ions there, and it was gamma carboxyglutamate residues that were responsible for binding to the calcium ions. Again, with factor 10 here, it had gamma carboxyglutamate residues which were binding to these calcium ions here to form this prothrombinase complex. Prothrombin, factor 2 here, it also had gamma carboxyglutamate residues in, and which bound to calcium ions, which then also bounds to the phospholipids of an activated platelet. And finally here, when 7 bound to tissue factor and formed this complex to convert itself into 7A, it also had calcium ions binding to gamma carboxyglutamate residues, which were then also binding to the phospholipids on the surface of our tissue cell here. Okay, so all of these coagulation factors, they contain this special amino acid, gamma carboxyglutamate, and it's really important for binding to calcium ions, which then also bind to phospholipids, and therefore informing these complexes on the surface of cell membranes. Okay, right. Now, when these coagulation factors are being produced in the liver, you have to put these amino acids in. You have to change the amino acid glutamate, which is one of the normal amino acids, into gamma carboxyglutamate. And this process requires vitamin K. Okay, and I want to now study this in more detail now. Okay, and therefore, if you are deficient in vitamin K, you cannot do this. So these coagulation factors will be built, but they won't get the glutamate converted to gamma carboxyglutamate, and without the gamma carboxyglutamate residues, they are non-functional, and therefore all of these coagulation factors are going to be non-functional, and of course, getting rid of those, I mean, here's from prothrombin, so if you've lost prothrombin function, then the intrinsic and the extrinsic pathway go down. Okay, so fibrin meshes aren't going to be produced, and the other ones are just going to make it worse as well. Okay, so of course the hemostatic plugs will be far too weak, and therefore you'll have problems actually preventing hemorrhage. Okay, so the first thing then that I want to do is actually draw out a picture of what a glutamate amino acid looks like and what a gamma carboxyglutamate residue looks like, and then we'll discuss why vitamin K is so important for this. Okay, so let me start by drawing out a glutamate residue. Now I will draw this as though it's in a protein. So I'm going to draw the residue rather than the free amino acid. So I'm going to have both the amino group and the carboxy group of the amino acid as though they're bound to other amino acids on either side. Okay, so let's do this here. So here then is the amino group of the glutamate amino acid. Then we've got the alpha carbon of the glutamate amino acid, then the carboxylic acid group, and this will be linked to the amino group of the next amino acid along, and this amino group up here will be linked to the carboxylic acid group of the next amino acid along. Okay, so then the R group of a glutamate residue just consists of an ethylene group, so 2 carbons with 2 hydrogens each coming off them, like so, and then we'll have the carboxylic acid group here, like so, which will usually, under physiological pH, have lost its proton and therefore will be in the conjugate base form, which is called glutamate. Remember, the actual form where you've still got the proton attached here, that would be called glutamic acid. Okay, but normally under physiological pH, most of the glutamic acid residues in a protein have lost their proton and therefore are called glutamate. So this here, this is the amino acid glutamate, and this is one of the normal protenergic amino acids, a really important amino acid that can be put in by ribosomes. Okay, now, in these coagulation factors here, they will start off with these residues, like so, and then what's going to happen is they're going to be converted into these special new residues that can't be put in by ribosomes and have to be produced by a modification of glutamate, which are the gamma-carboxyglutamates. So the core amino acid structure, of course, has not changed, so I'll just copy that out here. And now what are we going to change? Well, we're now going to stick a carboxyl group onto the gamma carbon. Now, what is the gamma carbon? Well, this is the old way of naming up the carbons in a carboxylic acid. The old way of naming the carbons in a carboxylic acid is you start off with the carboxylic acid group here, and then the next carbon along you call that the alpha carbon, so that's why I've been calling this one the alpha carbon. Then you'd continue going along, so you go on to this one will be called the beta carbon, so we're just using the Greek alphabet here, and then this one here will be called the gamma carbon. So that makes sense now. We're just going to have a carboxylic acid group coming off this gamma carbon. So let me put this in. So here, this methylene group has been unchanged, and then now off the gamma carbon we're going to have another carboxylic acid group, and again under normal physiological pH this will have lost its proton, like so. Okay, so you'll have two carboxylic acid groups, like so, and now you can see why this is absolutely fantastic at sticking to calcium ions, because it's got these two negative charges here which are going to bind to calcium ions fantastically, which of course is the function of these gamma-carboxyglutamate residues in these coagulation factors. So this is now a picture of gamma-carboxyglutamate here. Okay, right, so this has to be made as a post-translational modification to the coagulation factors. So you produce the coagulation factors 2, 7, 9 and 10 in your liver cells, and then some enzyme is going to have to go along and change certain of the glutamate residues into gamma-carboxyglutamate residues. What we're now going to study is what is the name of that enzyme. Okay, so the name of that enzyme is gamma-glutamyl carboxylase. Okay, so this process is catalyzed by an enzyme called gamma-glutamyl carboxylase, and when it does it, it requires at the same time a conversion of a form of vitamin K, which we'll call reduced vitamin K, into another form of vitamin K, which we'll call oxidized vitamin K. So every time this enzyme, gamma-glutamyl carboxylase, converts glutamate into gamma-carboxyglutamate, what's going to have to happen at the same time is, and I'll just bring this up, let me keep it in view, that'll do. Okay, it's going to also have to turn a molecule, a form of vitamin K, which we'll call reduced vitamin K, okay, and it will turn it into a form called oxidized vitamin K. Okay, and this will give up two hydrogen atoms. So when you convert reduced vitamin K to oxidized vitamin K, what you're going to lose, as in the normal sense of reduction and oxidation in biochemistry, is you're going to lose two hydrogen atoms, so two protons and two electrons, and these are going to go into this process. Okay, they're going to be important in allowing this reaction here. Okay, so without this conversion of reduced vitamin K into oxidized vitamin K, you cannot convert glutamate into gamma-carboxyglutamate. So when this is converted into this, you also have to convert a molecule of reduced vitamin K here into oxidized vitamin K. Now, of course, this will come to an end at some point. You'll use up all your reduced vitamin K, and it will now be in this waste product of oxidized vitamin K. So there's going to have to be some process that is returning the oxidized vitamin K into reduced vitamin K, and there is an enzyme which does this, which will be extremely important when we come on to the mechanism of warfarin. Indeed, warfarin works by inhibiting this enzyme. The enzyme is called VCOR, which stands for vitamin K oxide reductase. Okay, so this is vitamin, that's the V, and then K is for K, and then it's oxide, pertaining, which means obviously just pertaining to the oxidized form of vitamin K, and then it's reductase because it's going to return it to the reduced form. Okay, so every time the enzyme gamma-glutamyl carboxylase converts a glutamate residue into a gamma-carboxyglutamate residue, it also has to convert a molecule of reduced vitamin K into this oxidized vitamin K. Of course, we very quickly run out of the reduced vitamin K and we'd end up with all oxidized vitamin K. So there is another enzyme called vitamin K oxide reductase, VCOR, which converts the oxidized vitamin K back into the reduced vitamin K. Okay, so this is the normal process then by which we can actually add these gamma-carboxyglutamate residues into coagulation factor 2, 7, 9 and 10, and I will stress again that having those residues there is absolutely essential for the function of these coagulation factors. If you are vitamin K deficient, so you have far too little vitamin K in your body, then you're not going to have these reduced molecules of vitamin K, okay, or neither are you going to have the oxidized vitamin K. You've just got far too little vitamin K. So imagine this isn't here, okay, far too little vitamin K, then of course the gamma-glutamyl carboxylase cannot actually convert the glutamate into the gamma-carboxyglutamate because there's not going to be any reduced vitamin K because there's no vitamin K full stop, okay, or there's far too little vitamin K. So loads of these coagulation factor molecules will end up being put into the bloodstream without having had their glutamate residues converted into gamma-carboxyglutamate residues at the appropriate places, and therefore these coagulation factors will be non-functional. And as I say, clearly 2, prothrombin, is absolutely essential for both the intrinsic and extrinsic pathway. So if 2 is not functioning properly, then the intrinsic and extrinsic pathway are going to be hugely weakened. Okay, and therefore your conversion of fibrinogen into a fibrin mesh is hugely compromised, and therefore your hemostatic plugs are going to be compromised in their strength, and therefore you're going to have problems actually preventing hemorrhage from your broken blood vessel. Okay, so that's why vitamin K deficiency is going to lead to problems with the hemostatic process, and we will come back to this mechanism, in particular this enzyme vitamin K oxide reductase, because this is going to be the target of warfarin. We'll do that in the video on anticoagulants. Okay, so we'll have a break here, and in the next video what we'll start to talk about is thrombosis, okay, the pathological blood clotting process, and we'll also talk about the endogenous mechanisms that the bloodstream has in order to prevent hemostasis, the hemostatic machinery, from being recruited in improper circumstances. So we have talked about the proper circumstance in which hemostasis should occur. All of this platelet adhesion, activation, aggregation, and the intrinsic and extrinsic coagulation cascades, they are supposed to happen when you have a great big hole in the side of your blood vessel. Okay, what if they start happening inside a perfectly intact blood vessel? Well, that's what happens in pathological blood clots. That's called thrombosis. What we want to look at is what mechanisms does the body have to try and prevent thrombosis, okay, because there are a number of endogenous mechanisms it has to try and stop that, okay, so that's what we'll be doing in the next video.